Okay. This is the class of 255. Okay. Mathematics for software engineering. Okay. Software techs. Okay. Okay. So last time we know that when we have the number between base 10 and base 2, okay, we should be able to change or transfer the base 10 number to the base 2. Or if we have the base 2 number, we can change to base 10. 2 to base 10 is easy, okay? And base 10 to base 2 also easy. But only we have to take apart the integer part and the fraction part, okay? When we talk about the integer part is mean the number that stay in front of the decimal point, okay? So we have this part like a 101.1. Oh, this one is the binary point. This is the same thing. The number will stay in front of the decimal point or even the binary point. This give you the integer, okay? So this will give you integer is the number. And the one that stay after binary point or decimal point, this will give you the fractional part, okay? It's less than 1, okay? So that will leave it over there. So in the base 10, if we have the base 10, the number that you have the integer part, if we want to write down in terms of base 2, we will think about, okay, what is the multiple of 2? Add them together of some number like 2 to the first, 2 to the second, to the third, and so on, okay? We want to write down this integer part in terms of the multiple of 2, okay? That's how we come up with the base 2, okay? And then the fractional part, we can think like, what is the fraction of 2? Okay, what is the fraction of 2? That can be expressed in terms of this fractional part. So on the other way around, if you think about, okay, we have to think about what is the multiple of 2. So from base 10 to base 2, we have to think like, okay, so instead of multiply by 2, we have to divide it by 2, okay? And for the fractional part, instead of divided by 2, we multiply by 2. That's how we came up with all this way that the example that I gave to you, that if we have the number which is written in base 10 number, we will have to do 2 steps. We have to split the integer part. For the integer part, we have to do the long division, okay, to see that what is the multiple of 2 that we have for this integer. And for the fraction, for this fraction, how can we come up with the base 2 of this fraction? Instead of divided by 2, we multiply by 2. Okay. And then we keep all those 0 and 1, 0 and 1. And then we will be able to combine all those integer and fraction together. Okay. So let's just get the quick review like last time. Okay. Like we have this number 0.85843575. We multiply by 2, we get this number. We have keep 1. We write 0.1. And then we take only the fraction part, okay? This fraction multiplied by 2, we get 1.375. We keep 1. We take only 0.375 multiplied by 2, we get 0.75. And then multiply by 2, we get 1.5. And then multiply by 2, we get 1. And so we have this base 2. For this number, we have 0.84375 can be written as 0.11011 base 2. So this look okay, right? But I give you another example that, well, if you look at just the basic example, just only 0.1. 0.1 in base 10, I want to write this down in terms of base 2. So I will do the multiply by 2. For 0.1, I get 0.2. 0.2 multiplied by 2, I get 0.4. Okay. 0.4 multiplied by 2, I get 0.8. 0.8 multiplied by 2, I get 1.6. So I keep 1. And then I have 0.6 multiplied by 2, I get 1.2. 0.2 multiplied by 2, get 0.4. And so on. And so it's keep this loop. 0.4 times 2, 0.8 times 2, 0.6 times 2, 0.2 times 2. And so it's give back to this one, or you can think about this one. So you can see that we have infinite digits of base 2 number, okay? And this why it has some problem with the floating point number, okay? Because in the computer, we have only the finite digit of the space that we can store in the computer register in the computer. Okay, so let's see. Yeah, like they said here, it's important here because most of the real number cannot represent it exactly in the computer. Okay, this is just one example that we have this repeated. Okay, so just be careful that not every real number can be represented exactly in the computer. Okay, so now I would like to talk about what is the K floating point number. In this one, if we say that, well, I want to represent the floating point number, which can be expressed only by using the 3 number of the mantissa, can be stored only B1, B2, and B3, only 3 digits, okay? Up to 2 to the power K. K also 0, 1, and 2. So K is just 0, 1, 2, okay? Plus and minus sign, okay? So for this one, if I talk about, okay, what are numbers that can be represented using only 3 digits of the mantissa? This is all the number that I have, okay? So I get 0, 0, 0.00 to the power 2 to the power 0, okay? 2 to the power 1 to the power of minus 1, okay? So K is the exponent, which has only 0 and 1. And the sign is going to be plus and minus sign. These are the number that we have, okay? That can express using this system. And when I have put all the number in this system into the real line, you can see that there are the space between all these number, okay? There are space between this number because only the number that has 1 over 16, 1 over 8, 3 over 16, 1 over 4, this one can be stored exactly. But if some number, which is in the real line here, it depends, like they will round up, so it's going to use this number. Or if I have the real number here, we stay in the real line, okay? So in this computer system, it will use this number instead, okay? So it's rounded to the nearest number which you can use in the computer. So this is what I mentioned, that not the most of the real number cannot represent it exactly in the computer, okay? So this is how we have, okay. So now we talk about the floating point representation in the computer. So many binary computers have a word of length of 32 bits. Okay, it's typically, okay, and which is we call like is the binary digits. So normally for the internal representation of the number, we store it in the standard floating point form. Okay, what is the standard floating point form, or we call the single digit precision of floating point number? Okay, we will store in this way. Okay, this is the standard 32 bits word that store as a normalized floating point number. So we will store whatever the number, okay, that has the part of the mantissa, okay, which is Q, okay, the Q is represent the mantissa. And M here for the exponent. Okay. And most of the number, I will say that we will have, suppose I have just for the base 10 number or real number, okay? 2.52, this is one type, or 0.253, maybe the other one. Or we have minus 3.256 and plus and minus, and okay, yeah, what else? Okay. If we think about writing this one as the normalized scientific notation, okay, we will have 0.252 times 10 to the first, okay? And this number we have 0.253 times 10 to the power 0. And this one is again minus 0.0. Okay. If you have the number, something that you have to tell someone, okay, about the number, at least the first one, you have to tell that it is positive or negative, okay? So you have to know the sign of the values of the number that you want to represent. So it's either positive number, negative number, or positive number. So the first thing you have to tell or give information about this one is plus or minus sign. If you want to play a game or turn on something, I don't mind, okay? But just please turn off the noise. Okay. The first thing that you have to tell everyone about the number that you have is the plus or minus sign, okay? Number two, the other part information of the number is the part of the normalized mantissa. This is from the aircon or what? เสียงอะไรอะ aircon or fan or something? Is fan? Okay, I'm sorry. I thought that someone playing game in my classroom. Okay, I'm sorry. I'm really sorry. Okay. I really do. Okay. 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 And the third part is what? this exponent, okay? And the third part is the exponent. And the exponent, we also have the sign for the exponent is positive or negative, right? Because here is the positive 1, 0, positive 1, and negative 3. So for the exponent, we can tell either is 0 is the positive number or the negative number. So these are three parts of the number that we should store in your system, right? Because you have to tell the computer if it is positive or negative or 0, or what are the details, what are the number, which is the mantissa part, okay? The mantissa part play really important role because the more details you have, okay? So you know what are number you have, right? If you have, you can think like if you have this number, this fine. But if you have 0.2765321541176021213, something like this. So the more mantissa, the more details of the mantissa, it means that you get more details about your number, right? And also what else you have? The mantissa is also important because you know the number. And what else you have to tell about the exponent, how many digits that is shaped the 0, right? To the first non-zero, because whenever we have the number, we have to shift this, how many number that you shift. And then we shift to the left or to the right is going to be, the exponent is going to be positive or negative. These are information that we need to tell the sign of the number, the mantissa, and the exponent. And the exponent have to have positive, negative, or 0. Okay, everybody clear? Okay, now, some kind, right? So if we have, you can think about, if we have the slot of the 32 bits, suppose this 32 bits, you can think like, okay, this is the number that you have to, store. Suppose 32 bits. You will have to put the number in your slot. Okay, suppose you have all this space that you have to put 0 and 1, 0 and 1. Okay, now suppose that I want to tell the computer, so it has to be 0 and 1 because it's the binary. Okay, so how people can assign, okay, the computer. So you have to let the computer know that, okay, the first bit on the left, if we say that we keep it for telling the computer for sign. Okay, for the sign of the number is either positive or negative. The computer doesn't know positive or negative. Okay, and we have to assign it. And the people think about, well, if it's positive, okay, they look at the -1. If it's -1 to the power 0, it is 1, right? If I say -1 to the power 1, it is -1. So they will say that, okay, come on, if it is 0 here, it represents positive. If it is 1, this will give me negative number, okay? So it is going to be a convention that if something starts with 0 on the first bit, this will represent the positive number. 0 equivalent to the positive sign. 1 equivalent to the minus sign. Okay. So this first bit, we will use this one. Okay. If it has 0, it is positive number. If it has the number 1 there, we can tell that it is the negative sign. Okay. And in the standard, let's see. Yeah. In the standard normalized floating point number, they originally they say, okay, I will reserve the first bit for the sign of the number. Okay. And we will store the other 8 bits for the exponent. This one for the exponent. One. Oh, no. 32 bit for the mantis. Q is the mantissa. M is the exponent. Okay. So first bit, 0 or negative 1. Okay, 1. Okay. So for the standard one, okay, let's see. The first bit already assigned. And then the other 8 bit for M. 1, 2, 3, 4. And the rest gonna be okay. The rest gonna be mantissa. So you reserve it 8 bit for the exponent. And then remember that the exponent part also have the positive or negative sign. So it means that for the standard way that you have to reserve the first bit, the second bit here on the whole length, computer word length, to sign of the either 0 or 1, this one, for the sign of exponent. Okay. And then this part, the last one, the last 23 bits is reserved for the mantissa. Okay. The normalized mantissa, which means the first digit after the binary point. Okay. So you store in these 23 bits. 23 plus 8 is 31. 31 plus 1, which is the sign. So you have totally 32 bits. Okay. Suppose you have the number. Okay. Let's see what the number that we have before. Let's see. Sorry, okay. Okay, so let's just work thing out, okay? Example, if I want to write the number, what should we do? 33 0.215. Okay. I want to write this down in 32-bit standard. More like floating point. Okay. So I will store the number in my 32-bit standard normalized floating point. Okay, the machine that have this form. Okay, the architectural design by using this standard normalized floating point number. So we will have to rewrite this 32.1215 in terms of base 2 first, right? So we have to convert this to base 2. So first step, we will split it up into 33 and 0.215, okay? So we have to divide the whole thing by 2. Okay, so you will have to keep doing this, okay, until you get number 1. Okay, if you end up having number 1, you stop. If not, you keep doing this. And how many times that you have to do the most? How many times? At least 23 times, right? Because you have 33 bits. No, 23 bits. Okay, 23 bits. So you will say that 0.215 equal to, let's see, 0.0011, 0.111100, and so on. Okay. I haven't finished it. Okay. But this is how you do it. And then the whole number would be, so 33 equal to 1, 0, 0, 0, 0, 1. Okay. When you combine them together, so you will get 1, 0, 0, 0, 0, 1 point. This is the number that you use to represent 33.215. Okay. So the first part here is come from 33. The second part come from 0.215. Okay. You combine these two together. The first part, oops. Okay. So the one in front of the binary point come from the number 33. The one after the binary point come from above, which is 0.215. But this is not written in terms of normalized binary form yet. So now you have to move the binary point to the left, okay, to the left. So it is, let's see, I'll have to copy this. Okay, so it's gonna be 0.1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0. Okay, I haven't done that part yet, okay? But this is gonna be your, you need 23 of them. But this one multiplied by 2, sorry. You move the binary point to the left, 1, 2, 3, 4, 5, 6. 2 to the 6th, okay? Now you have to make your exponent equal to 6. In base 10. But in order to store on the computer, you cannot store any of base 10 number. So you have to change number 6. And 6 is the integer because it's the number, okay, of point that you move, okay? So now you have to change number 6 to base 2. Six is 110 base 2. Okay. And this exponent is positive. Now, when I want to combine into the 32 bits register, suppose that you have okay. So the first bit, since this number 33.215 is positive, so it is the positive number. So we store 0. And now the next 8 bits. for the exponent. For the exponent, we have positive 6. So we have the positive 6. Right? So we put 0 because it's the positive exponent. And then we will store, okay, since number 6 is 110. So we'll store 0, 1, 1, and the rest you plug in 0. Okay, because number 6 is 110. Now, the rest you have to plug in your mantissa part. Okay, 23 bits. So you plug in 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, and so on. Okay, but you can store only 23 bits. Okay, this is how you store in the just the normal one, the standard one. But there are also the problems because in the old days, some computer company have the different design, okay? Because some company they give more emphasize on the more number of bits in Mantissa. So they said, okay, I use 24 bits of Mantissa. Some other use 23 bits for the Mantissa. Some might use 22 bits for the Mantissa because they have different design, different way to design their computer. And then when you change the platform, change the model, so you cannot remix, cannot use the number or the calculation from other architecture, okay? So they have get together, okay, by the IEEE, IEEE. So they sit together and set the standard ways to store the computer instead of doing this way, okay? And some of you might confuse because if you read different textbook, some textbook reserve only 7 bits for exponent. Some book might use 8 bit for exponent. So don't be confused because this is not normal. It's normal because it's not the standard way. It's before the convention, before they get together, okay? But this is not efficient way to store the number. So they have the other way that they talk about the standard IEEE, IEEE. They gather all the smart people, okay? They come up with this model, okay? They also have 32 bits. They make 1 bit for sign. Actually, they split into 2 parts. They talk about Mantissa and the what they call the values of F, and I will tell you what is the F and what is the value C that they store. Okay, so they have, so radix point is, maybe we talk about similarly to the binary point. Okay. Okay, don't worry here. So in 32 bits, the whole thing. So the first thing here is not changed by the sign of the mantissa or the sign of the number, okay? You still need it. And so totally on the left here, so you have 1 for the sign of the number, or we can call the sign of the mantissa. And you have 8 bits here, okay? I will not explain it yet. They will have one word here, this called biased exponent. So, but it's still, you use 8 bits for the exponent, okay? But you have biased exponent, but I will tell you later. And now, you know that whenever we have normalized form, we always know that the first bit is 1 because we will move to the left until the first bit after the binary is 1, not 0. Okay? And they said, why should we store the number that we always know the information? Because the first number after we do the normalized floating point form, the first number always 1. So we ignore that part. We will not store number 1. Okay. So they will do that. They move instead of, okay, let me copy this number. In this form, for the last one here, instead of move here as the normalized floating point number, because as I said that we always know that the normalized floating point number, the first number after the binary point must be 1. Okay, so we don't want that. We want to write it in the way that we know it is 1. So we get 1 point. I have to write down here like 1.0. Okay. So the first number 1 in front of this Reddit point, we will store. It means that instead of store 1 0 0 0 0 1, we store 0 0 0 0 1 1. Okay. So you can save 1 bit. Keep in mind, the more information you plug it in into the 32-bit limit, we have limited space to plug in the number. So we try to avoid to store the unnecessary information in that 32 bits. And one that we can avoid is number 1. Okay. So we store only. So we call here as 1.f. So this f part is mean the rest of this part. Okay. Or the number after 1 point. So we store only f. So that is why we say f here. F is from plus mantissa. Okay. And this is very clever. Every time when I come to this, but how come people in the old days, they're so smart? Okay. It's amazing idea. Like you remember that for the normalized form, you have 8 bit, but those 8 bit, you have to save 1 space for the sign. Either is positive or negative. Okay. So the largest number that you can store is only 7 bit. That you can store information. Okay. So you can think that the largest number is the 2 to the 8 plus 2 to the 7 plus 2 to the 6. Okay, you will see that the largest number that you can store here is gonna be 1, 1, 1, 1, 1, 1, 1, right? Okay, so it's gonna be 2 to the 1, 0 plus 2 to the first plus 2 to the square plus 2 to the third plus 2 to the fourth. Am I right? 1, 2, 3, 4, 5, 6, 7. So this is how you will get the largest number, right? But if we can use the all of them 8, you will have to add more. You will have larger exponent. Okay? The standard form, you add them up, you have only this part as the number for the exponent. And keep in mind, number for the exponent is mean you multiply by 2 to the power of something, right? So here, if you add 2 to the 8, and it means that how many digits that you have to add more? You have a lot more, right? 2 to the 8. So you add them up. So it means that you have many more digits that you can get involved, or you get the larger number in your system. Because in the real line, you can see that you have 0, you have plus infinity, you have minus infinities. Okay, this is for the real world, real line. But oh, because it's linked to my watch. Okay, so this one, the standard one, you can store only 7 bits for the number for the exponent because you lost one bit for the sign. Okay, but here this is very smart because they will do this. Okay, they will call it, they will store the values of C. What is C mean? C is called the bias exponent. Why is this that? Because they will think about, okay, if I'm stored in this way, if you have something like C, something to the power of C minus 1 to 7. Let's do some mathematics, okay? Just work on the mathematics. If you have number 2 to the power 0, 2 to the first, 2 to the second. Do this calculation for me, please. What is it? To the 7 plus 2 to the power 6. Five. Is that right? All right. 255. Okay. 255. So if I store number 1, okay, to the whole thing there, and I can see that now. If I divide it by 2, what is it? Right? But actually, if I have 8-bit, I install number 1 all the way. I will reserve that for the infinity because it's the largest number that I can store. Okay. If it's more than, if I say my 8-bit, if I say, okay, plus or minus for the first one, 1, 2, 3, 4, 5, 6, 7, 8. All this 8-bit. Okay. If I store number 1 for 8 of them, I will reserve that for my infinities. Does it make sense? Because my real line, 0 and plus infinity and minus infinity, we cannot do it. But with this, I will have the largest number that I can store. Okay. And we will do that. If I reserve all the number 1, 1, 1, 1, 1, 1, 1, 8 of them, the computer might know that, oh, okay, that's larger than the largest number that I have. Okay. Because that's reserved for plus infinities. And we will say that it's infinities. So the one less is gonna be 1, 1, 1, 1, 1, 1, 1, 1. And if I put 0 here, this is gonna be my largest number of the exponent that I have. Okay. So 1 less. So I gonna have subtract 1, which is mean this gonna be 0. So it's 254. And then 254, if I divide it by 2, I get the number 127. Okay? 127. So I will say that, okay, if I say that the whole thing here, if it's greater than 127, the whole number that I can store, the largest if you have 111 is 254. Okay. If I divide it by 2, I will set 0 here. If the number greater than 127 is going to be positive. If it's less than 127, it's going to be negative. So my exponent will be something go up into 2 to the power 127. Okay. 127. So I will store only the C part here. Okay. It means that I will scale my number instead of put 1 unit for sign, 1 bit for sign. I will do in this way. And I will say that, okay, I will keep the number C. Okay. If C greater than 127, it's going to be my positive number. If my value C less than 127, it's going to be negative values. Okay. So this is how I will store the values of C. Let's see. Okay. So I will use the same number here. Now, my F part, okay, I will have plus and minus part of my mantissa, okay. Multiply, no, I have to say plus and minus 1 point F. F is the part of the mantissa. Multiply by 2 to the power of C minus 127. Okay. So from this one, if I have my number, originally I have the number 1, 0, 0, 0, 0, 1, 0.001101100 and so on. Okay, this is my number 33.215 base 10 can be written in base 2 like this. And now, if I want to write this in terms of the IEEE 32-bit notation, I will move this only after number 1, okay? I will not move all the way in front of 1 because I know that the first one must be 1 already. I will store only F part. So it's going to be 1.00001. So it's how many points that you move? Only 5, right? 5. Now, what is your F part? This is going to be your F, okay? This is your exponent. But you will say that, okay, I will not store number 5. I will say that I will store value C. And we know that C minus 1 to 7 in this case is 5, okay? So my value C is just 5 plus 1 to 7, which is 132, my C. And now I have to write 132 in terms of base 2. When I write down in terms of base 2 is 2660 to 330. And what was that? It's gonna be, I copy. Okay, so it 132 is 1 0 0 0 0 1 0 0. Okay, 1 0 0 0 0 1 0 0. So now I get C part. And this number is the positive number. So the first bit is going to be, so let's see. First bit is going to be 0 because it's positive number. And then 8 bit, 1, 2, 3, 4, 5, 6, 7, 8. 8 bit store C. So it is 1, 0, 0, 0, 0, 1, 0, 0. Okay. What else you have? You're going to have to copy F part, F here. Okay, you can see that here you can store number 0 first. C is just the bias exponent. And then F is this part. Okay. So you want to see one more example? How we do it? Okay. So you all help me too, okay? So right now, just think about what is the number that we have. Okay. Suppose I have this, okay? Let's see. I want to. So you guys copy the the number already, okay? I want Microsoft Excel. They did not store Microsoft Excel in here. Don't worry. Maybe this too much. I think this is. If I don't have Microsoft Excel, I will not do it. Okay, maybe just 0.012. Okay, I'm just a little bit lazy, so clear. Okay, so if I want to write this down in terms of IEEE 32 bits, okay, since this one has only the fraction part, so I just 0.12. So this is the number that I multiply by 2, okay? So 1.2 multiplied by 2, I get 0.024. Multiplied by 2, I get 0.048, okay? So something that I just multiply by 2. And it just... Okay. So I will say that I will have all of these. Okay, go down. Okay, it's just like this. Okay, so now I will say that it is equal to 1.1000010 and so on. Okay, this is, you have to keep doing that. Time to the power of what? Minus what? How many? 1, 2, 3, 4, 5, 6, 7. Okay, 7 point minus 7. So this part is your F, and this part is your C. No. C minus 1, 2, 7 is equal to minus 7. So your C is minus 7 plus 1, 2, 7, which is 1, 2, 0. And you can see that this C is 1, 2, 0. It means you have the negative sign for the exponent. Okay. As I said that at the beginning, you have 1, 2, 7 is as like the 0 at the center. If it's greater than 1, 2, 7, it means you have the positive sign. Okay. And the largest exponent you have 254, right? 254. That's the exponent up to. So C is 1, 2, 0. So you can write down 1, 2, 0 in terms of the base 2. So just 1, 2, 0, you have the long list. So C equal to 1, 1, 1, 1, 0. No, 1.ถูกไหมเนี่ย Am I right? Yeah. Okay. So I have C equal to this. Okay. So this number is positive, so 0. You have 1, 2, 3, 4, 5, 6, 7, 8. So you get 0, 0, 0, 1, 1, 1, 1, 0. Okay? So you have 8 bits for these values of C. And then what else you have to store? Instead of 1, 1, you get 1, 0, 0, 0, 1, 0, and so on. Okay. This A part put here. This C part you get here. Okay. And 0 here on the front is the positive sign. So that's how we store. And you see that this is just simple things that I will point it out that you will normally restrict 0 and 255 is reserved for the special case. If you put everything 0, it means 0. If you have plus and minus infinities, so you know that the values of C lie between C minus 1 to 7. It have to be like, if it's 0, it's gonna be negative 1 to 7. Okay, and you can see that the largest representation, if you write this down, so you can see that it can be the largest number that this 32 bits number can store is just only 3.4 times 10 to the power 38. Okay, and if it's negative number, this is going to be the smallest positive number that is can be stored. Okay. And if you say that, oh, that number is not small enough or large enough so that it fit our computation. The other ways around, they have like the double precision, okay, in your calculation. If you use double precision, it means you have 36 bits. But on that 36 bit, they will reserve one bit for the sign of the mantissa. As always, because the number you have positive and negative. So you have 1 bit reserved for sign mantissa. And you reserve 11 bits for the bias exponent. And you have 52 bits for the fractional part of the mantissa. So you have larger bits. So it's gonna be larger number. Okay. And I think that I will post this one and you can study and look at the example from this slide. Okay. And I think that 2 minutes late, but it's okay. All right. So I hope that, do you want to read it by yourself or do you want me to go through this? No? Okay. So you just look at this example, this one. Yeah, this is just the other example that is in this slide. Okay. I put this slide up in the file for lecture number 1 and number 2. Okay. So I think this is all for today and see you on Friday. Okay. Thank you. Okay. Keep in mind that the link for the Zoom, it lasts only 7 days. Okay. So if you cannot catch up, you better do it tonight or tomorrow night before it's erased. Okay. Don't worry. Okay. I will send the link and you can follow that. Okay. Okay. Thank you. Okay. Okay. Sure.
View.
Okay.
So this is about 8 is about the community.
B, the value C. But, yeah.
And I'm talking about this app.
F. Okay. Oh, this is your part of the mantissa, right? And you move this to the one after number 1.
Yes, I got it onto there, but I'm not
And this
sure.
one is F.
I'm not sure if where does this one go? If
It everybody under the when the calculation, okay, they know that this number 1 is always 1. So in the computation, they know that it is 1. So we ignore that. And everybody understand that 1 must be there. And this is only the F part.
So if the computer,
You add one.
if I use this formula,
Mhm.
computer will know that integer is going to be always one.
Yeah, the first one is always one.
So they just pretend.
We just, okay, if everybody understand the same thing, why should we store? Because we want to save the space. We have only 32 of them, right? Everyone understand the same thing. Okay, just leave it. We just store only one here, so I have one more space, you know. If everyone say point one, like the one before, the standard, you make it like normalize floating point binary number. You have the first point after the binary have to be one in the way that is normalized. Okay, and since we know that you have only 0 and 1,
Yeah.
the first one must be 1,
Yeah.
so we not store that. Yeah, it's because it's normalized. That makes sense.
Yeah. Just
These
for-
people is so smart.
Get more precise.
They try to save things. Yeah.
I see.
Good.
Yeah.
Yeah, thanks. That's good.